This video is on one of my favorite topics of the entire course, which is reactive energy balances. And it's one of my favorites because it encompasses almost everything that we've learned so far. So I've titled this video The Recipe because it'll go through the steps of how to perform a reactive energy balance. So the process unit that we'll be looking at is a reactor, which will convert some reactants to some products. And I've drawn in a heating coil here. So there's some amount of heat that I either have to provide to the reaction or take away from the reaction. So again, here we're not to chapter 10 yet. So we're going to still assume that it is at steady state. And therefore the temperature inside the reactor must remain constant. Step one is the same step that it was for non-reactive energy balances, which is to perform all material balances to the extent that you're able to. Keep in mind that this takes into account performing a degree of freedom analysis. So nothing changes from that respect. We're going back to chapter 4 stuff where again we have to figure out a material balance for a reactive process. Performing a degree of freedom analysis, so counting all my unknowns, material balances, taking into account how many reactions I have. So if there's a reaction, I have to do squiggle or atomic method in order to figure out what the flow rates and the compositions are, or what the flow rates of individual components are. And step 2 diverges a little bit. So there's two alternate methods that you can follow for reactive energy balance. So I'm going to draw it kind of in a flowchart fashion. So the first flowchart would say, if there's only one reaction and you know what the heat of reaction is. If only one reaction and heat of reaction is known, the standard heat of reaction is known, then you would do what is known as the heat of reaction method. Heat of reaction method. If, on the other hand, you do not know what the heat of reaction is, or if there are multiple reactions, if multiple reactions, or heat of reaction is unknown, then you're going to want to do the heat of formation method. So kind of two alternate methods. Once again, it's up to personal preference, although not really to the extent that the extent of reaction or the atomic method was. You should really follow this flow chart that if you have one reaction and the heat of reaction is known, then the heat of reaction method is going to be simpler. But if you have multiple reactions or you do not know what your heat of reaction is, then your heat of formation method is going to be much easier. So after you choose which method you want to use to solve the problem, you can then proceed from there. The main way that these two methods differ is what you set your reference state as. So in the heat of reaction method, your reference state is going to be, remember, you can choose one reference state for each species. So your reference state, I'll say states because you can choose one for each, choose a state for each species. And when I say a reference state, I mean what temperature, pressure, and phase of matter. So in the heat of reaction method, my reference state is going to be the species at 25 C and 1 atmosphere, and whatever state for which I know the heat of reaction. Okay, so once again, if the heat of reaction method is chosen, you want to choose for all species 25 C, 1 atmosphere, and whatever phase the species is in for that known heat of reaction. And the reason for that is your heat of reaction is probably going to be known at the standard conditions, which are again 25 C and 1 atmosphere. So in order to perform that reaction, all your species have to be at this reference state in order to cross the bridge, is my analogy for it. So in order to convert those reactants into products, they have to go to 25 C and 1 atmosphere such that you can use this heat of reaction in order to convert them. In contrast, in the heat of formation method, my reference states are going to be the atomic species at 25C and 1 atmosphere. So I misspoke a little bit just there, not the atomic species, but rather the elemental species. So again, choosing whatever form that atom is found in nature. So elemental species at 25C and 1 atmosphere, and then it goes without saying of whatever phase of matter that element is found in nature. Now, due to how I've chosen the reference states, this is going to change the equation for delta H. So also kind of going without saying, if I go all the way back up to the beginning, if I cancel the terms of my energy balance, I'm assuming that I'm going to get Q is equal to delta H. Or even if I do have other terms, right, figuring out what Q is has to do with what delta H is. So in order to find Q, I have to find what delta H is. And both of these methods, the heat of reaction method and the heat of formation method, are going to tell you what delta H is. So in the heat of reaction method, delta H can be written in the following way. It is going to be the sum of the outlets. So sum of, for the outlets, n dot out times H hat out minus n in H hat in. And then I also have to add the extent of reaction times that that standard heat of reaction, which I know. All right, and for the heat of formation method, it's going to be a little bit simpler. And the reason why it's simpler is because I don't have to account for the heat of reaction anymore, because my reference states are the heats of formation. So delta H dot in this case is going to be the sum of the outlets. So n dot times H hat for out minus sum of n dot in H hat in. And I'll just put in parentheses that delta H hat R is not needed since elemental species are the references, are reference states. Step 3 is going to be forming that table. So I try to teach you that this is worth it to you to do for non-reactive energy balances. And some of you might have resisted that urge to make the table. Now with a reactive energy balance, a table just becomes that much more necessary for keeping yourself organized. Make an inlet-outlet table. And a good table should have the following elements. You should have your species, obviously, and you should list all species in the process. So whether or not it's a product, a reactant, or just an inert molecule. So products, reactants, and inerts alike all need to be in this table. You should have an in section where you have mole per second, or flow rate in, and H hat in. And you should also have an outlet section, flow out, H hat out. And your table should also state what the reference is. So this is, again, just to keep yourself organized, state your reference. And organization becomes so important with these problems because there's so much going on. The flow rates I would fill in. My H hats I would also fill in. So H1, H2, H3, so on and so forth. All right, and the reason why the expression for delta H changed up here for the two different methods is because your method for calculating the H hats will change as well accordingly. So for the heat of reaction method, make myself a little table again, or a little partition. For the heat of reaction method, my delta H's are The reference state is the species itself. The heat of reaction method, remember my reference state are all the species at 25 C in 1 atmosphere. So all of these H hats are going to refer to the process of changing those reference species from the reference temperature and pressure to the process temperature and pressure. So let's say that my products up here are at, instead of 25 C in 1 atmosphere, they're at 60 C and 2 atmospheres. Well, because all of my reference states are 25 C in 1 atmosphere, all of my H hats are simply going to change from those reference states to my process, which I just said was 60 C in 2 atmospheres. So bringing back in methods from chapter 8, so Cp delta T and V hat delta P if it is a liquid, for figuring out what the enthalpy change is. And you might say, well, that seems like a lot of work. So instead of setting the reference state at 25 C in 1 atmosphere, why wouldn't I just set my reference state to be the conditions themselves? Because then I could cancel it out. So why wouldn't my reference state be 60 C in 2 atmospheres? And the answer to that is because the heat of reaction is not going to be known for that temperature and pressure. The heat of reaction more than likely is going to be known for standard conditions, which are 25 C in 1 atmosphere. So therefore, in order to use it, I have to have 25 C in 1 atmosphere as my reference. And then furthermore to this point is that I might have multiple process temperatures and pressures in my process. So while my product stream may be at a certain temperature and pressure, it's possible that my reactant stream or my inlet stream may be at a separate temperature and pressure. And then therefore, I can't pick and choose necessarily if I have a reactant coming in at one temperature and pressure, and then the unreacted reactant leaves at another temperature and pressure. I'm going to have to do this regardless. So it's best to just keep the reference state at 25 C in 1 atmosphere. For the other side, for the heat of formation, remember my reference state now is elemental species at 25 C in 1 atmosphere. And what this means is that in order to find the H hats, I first need to form the species and then change it to process temperature and pressure. So this is another reason why I don't have to take into account the heat of reaction in this formula. It's missing because it's built in to what these H hats are, or it's already factored in when I'm calculating the individual H hats for each species. So I'm not going to go through an example problem in this class period, but I do encourage you to read section 9.5 because there's a couple of really good examples. So they take the same process and they work it out in 2 different ways, and it really starts to illustrate what the differences are between these 2 methods. And then next time in class, I will prepare an example problem that we can go through in kind of the same manner in both ways to illustrate what the differences are. That's all for this video. Thanks for watching.